thanks for that great introduction, and thanks to the session conveners and all the sponsors for bringing me in today. I have the luxury of, at the Air Force Institute of Technology, working with about 15 students every year on research projects. So I was able to be opportunistic and try and pick a project that I felt kind of fit the theme of the day. And so I'm going to present on something that was some work that was actually done with myself, a couple of co-collaborators, and a student, and I'll kind of give them their due credit at the end of this. So for those of you who don't know, the Air Force Institute of Technology is located on Area B at Wright-Patterson Air Force Base up the street in scenic and lovely Dayton, Ohio. And for those who kind of don't know what we do, if you think about the Air Force Academy, right, that has degree granting authority for undergraduate students and has like a Division I football team. We are the graduate school component of that, probably more likely to have like a professional chess team. Though we don't, but we do masters and PhDs there, and we are hyper-focused on defense research, right? So the education that we provide is always APET accredited, so it's very similar to what you might get, say, if you were going to get an aeronautical engineering degree or a master's of science in engineering management, like I offer in my program. It's the same degree, just with defense-focused research. And so what I kind of want to start with talking about is the idea that as an engineering manager, as a civil engineer by trade, in the Air Force, it's a larger umbrella than what you might think of as like a core civil engineer, right? So roads, bridges, facilities, water and wastewater system conveyance, right? In the Air Force, we think of civil engineers as folks who do all that, plus we do facilities operations and maintenance, so electrical systems, HVAC systems. Essentially, if you picked up an Air Force installation, tipped it over and shook it, anything that would stay attached to the ground was something that a civil engineer is responsible for in the Air Force. So just kind of to set the stage there. So as a civil engineer, I'm going to talk about skillful, meter-free, hourly energy consumption forecasting for building and campus managers, but I've distilled it down to a basic question. Is it worth installing meters at each one of your facilities? Because isn't that all the rage, right? If we can meter something, we should, because we can collect data, right? And so I'll answer this question kind of throughout the presentation. I'll kind of spoil it by saying, I'll give you the graduate answer. It depends, right? It depends on your span of control and a lot of other things, and I kind of intend to improve that throughout the presentation. But one thing that we are always referred to as civil engineers in the Air Force is facility managers. And anybody who's in the facility management business knows that that's a really tough job. Or if you run your facilities for a facility that, or for a company that produces some sort of widget that is not tied to what you do as a facility manager, your budget or your proportion of the budget is likely highly calculable, right? So like when we need to be able to produce, better looking Tesla cars or be able to put forward a better project, where do they come looking for budget space, right? Facilities operations and maintenance. I know that on an annual basis, if I'm running a facility or a set of facilities, that I'm going to need to buy, say, air filters for my HVAC systems, right? And I know pretty much how many of those I'm going to need. But my bosses, who are not civil engineers by trade, know that they can take risk in facilities preventative and corrective maintenance for years on end, right? They can take a risk in those areas to be able to produce what they want, right? So our budgets are really limited in most cases. They're variable interannually, right? Depending on the bottom line of the business, those budgets could be variable. And they're really colorful. They're the first things that the bobs who sit in the corner offices usually come for, right? Facilities operating. But we also contend with unexpected costs. And I'm not just talking about corrective maintenance, like you have an entire HVAC system fail, like just happened in our building at Apple. 300 people working in a building, and we are in a involuntary no heat, no cool season, so we're saving energy, but not momentarily. And it's really hot there, so I'm happy to be here today. And then the third thing that I would say is there are some stochastic elements to our budgets that strain our budget prediction accuracy. Right? So what I mean by stochastic is that there's some random components or some really unknown components, and one of those is energy use, right? So I call this maybe something pseudo-stochastic, meaning there's a random component to it, but there's also a stable or a more predictable component to it. So imagine you're drawing in two-dimensional space, right? And I tell you to draw a line between the bottom left-hand corner of an XY plane and the top right-hand corner. But I tell you to kind of move your hand as you draw to that upper right-hand corner. We know the general direction we're heading, but we also know that there can be some variability associated with it. That's a pseudo-stochasticity. That can be somewhat predicted. I kind of know where we're headed, but there are some variabilities that I want to think about. And so what I'm showing you here is energy consumption at a half-hourly scale for Wright-Patterson Air Force Base for 3 fiscal years, fiscal year 2016, which actually starts in October of 2015, right, and it kind of goes through the middle of 2019, or September 2019. And so what I mean by the stable component of energy consumption is that we have some interannual predictability, or what I'll refer to later as periodicity, right? So if I kind of build out here, if I were to draw lines at January 1st of each year, I could probably pretty reliably fit a curve that looks something like that. Again, that's not the actual curve, this is just me playing around in PowerPoint, right? Using like the little curve fitting tool. But you can kind of see that periodicity to energy consumption. Lots of consumption in the summertime. You'll see where we're doing lots of facility cooling. We have our shoulder seasons where maybe we get a little bit of a break, and in winter we typically see a peak again. But if I were to draw some horizontal lines, kind of at the bottom of my energy consumption at the top, so that the peaks and valleys, you'll notice that the peaks don't always align, right? So in 2016, it looks like we had some really high periods of time where we were consuming lots of energy at a half-hourly clip, which kind of align with a warmer summer. And then you'll see some winters, 2018, 2019, where we actually had quite a bit more heating demand in our facilities. And the question is whether or not we can be skillful with the prediction of these kind of stochastic elements here. And again, I'm presenting this data at 30-minute resolution. Right? So the Air Force Base is tracking, rather DP&L is tracking the Air Force's energy consumption at a 30-minute scale at the installation level, so aggregated. So this would be all of the energy consumption across all of Wright-Patterson's facilities. But the DoD, kind of at a larger level, really since the last administration left and the new administration came in, is starting to at least actively recognize climate as a national security threat. And the citation I used there is the National Defense Strategy, which President Biden put out in March of 2021. And my guess is that most of you have seen a plot like this or something similar to this before, and actually Ms. Costello talked about it this morning. The IPCC, the Intergovernmental Panel on Climate Change, has been really active over the last 20 years in looking at our carbon footprint and the amount of carbon that's being emitted into the atmosphere. And they've produced projections that kind of go out to the end of the century and into the next century. And they typically align, if we look at it kind of deterministically, along 4 different pathways that are called representative concentration pathways, so RCPs, as I'll refer to them from here on out, with really aggressive ones where we do, say, nothing to curb climate change, where we emission of carbon into the atmosphere, that'd be RCP 8.5, and then less aggressive, or maybe you could think about it in a more optimistic way, more aggressive kind of installation or interventions to be able to reduce our carbon footprint. But the question that the government is asking, or at least the DoD has asked us to look at, is how is that going to affect what we know to be some of the determinants of our energy use, like solar radiation affecting our facilities, cloud casting, wind speed, precipitation, temperature, and how those things might affect our energy consumption. I should mention for a minute, though, how the Air Force and how the DoD really approaches their energy budgets, right? Because it's important to know how we approach that. So, like anybody, like you at your house, it's a must-pay bill, right? If you don't pay it for long enough, they come and they shut it off, and then it's like, okay, maybe I should stop eating out at lunch every day so I can pay my bill. So the Air Force treats this as a must-pay bill, which means that even though every year, every Air Force base across the enterprise has to come up with an energy budget, those energy budgets are typically last year's energy consumption times 1 plus the inflation rate, right? Probably in the ballpark, because there's that known aspect of the periodicity of energy consumption. But we have those years, if I were to go back a couple of bullets here, you can see where we had some years where we had some above average energy consumption in the summer, and some above average energy consumption in the winter time. So they're interested in understanding how that happens, because when they miss, and specifically when they budget too little money, to set aside too little money, or too little funds to be able to pay that bill, they have to rob it from somewhere else. And they're not going to take it away from the fighter pilot's Bitcoin. They're going to come after other areas of our budget, and where they take it out is something we call FSRM, or Facility Sustainment, Restoration, and Modernization. Essentially, the other money we have to maintain and operate our facilities. Right? So it's a huge concern when you think about that across the enterprise level, where our energy budgets are in the billions of dollars per year. Small errors can mean big backlogs in facility facility maintenance. So that's kind of motivating that question there. So the big questions that we set out to answer in my research group, and this is kind of what I do in a lot of my research, is like, I call it like forecasting, and not descriptive statistics, but like explanatory statistical modeling, is I always want to understand why things are happening the way they're happening. So my first goal was to be able to explain the determinants of energy use. What is it about Wright-Patterson Air Force Base, the people, the facilities, the exogenous influences like temperature that might be controlling energy use? And if I can put a handle on those or understand how predictive I can be in those, could I create a model that's skillful? Meaning that it could be something that would provide us enough surety that I could predict our energy use at any given time during the day to be able to make some sort of management decisions, which I've said here in more eloquent terms, and an actionable temporal resolution or time resolution. Right? Remember, I have 30-minute data. And then finally, this is the forecasting element of it, thinking about what the future might look like if we find something like temperature is really important for energy consumption. Can I use projections of future temperature to forecast what future energy use might look like and how that might affect our budgeting, right? And not just thinking about budget accuracy year to year, but also escalation, right? Because if we're going to end up paying an extra $7 million a year potentially in energy consumption, what are we doing now to think about what decisions we should make or things we should implement, like photovoltaic systems, or maybe divesting of facilities and infrastructure to be able to stabilize our budgets? Because I don't think the DoD is really thinking about how this is going to increase over time. So those are kind of the research questions that I've outlined in my series. So I want to convince you that Wright-Pat is a suitable case study. And this kind of goes back to my role as a civil engineer and an engineering manager. I'm not involved in like hypersonics or space vehicles. That doesn't really have any like meaningful relevance to folks who are practicing out there in industry. What I do is, I believe, pretty relevant to maybe what you all are doing with your facility managers, right? The Air Force bases are just an analog or analogous, really, with large communities or other campuses. So think about it like Wright-Patterson Air Force being no different than Ohio State University, right? A big cluster of buildings that we're trying to manage efficiently, or a hospital campus, or maybe an Amazon campus or something of that nature, right? But within Wright-Patterson Air Force Base, we'd say it has city equivalency. It employs 30,000 people. That's 30,000 people going in and out of like 3 or 4 gates a day, which is crazy. And we have almost 27,000 facilities on the installation. So maybe a little bit larger than the standard control state for the city government. But we also have some energy source diversity, and I won't get into it here, but we just had a paper published that talked about the transition between coal burning at Wright-Pat to generate steam to heat our facilities to natural gas, or primarily natural gas. But we use coal and natural gas, and then we have commercial power that comes from DP&L. And then we have some operational diversity too, right? So it's not just like we have mission facilities that are hiding all the aliens, right? We have residential, commercial, industrial, and then also government support activities as well. So we're operating around the clock, but certainly, as you can see from this plot that I brought back up here, we have peaks and valleys throughout the day and then throughout the year as well. So I'll kind of spoil it for you. We found through statistical analysis that it's really 3 things that seem to control our energy use at the installation level. There's temperature, periodicity, the idea of kind of that annual cycle of energy use. And if we look at it at finer resolutions, even the daily cycle of energy use, and time, right? What time of day is it? We use dummy variables to be able to unpack that, right? So it's not as dumb as it sounds, it's just using binaries to make it work. So those are kind of the 3 major variables that we used in a statistical model to be able to predict what energy consumption, or explain what energy consumption would be like at Wright-Patterson Air Force Base. Temperature, the underlying signal, which is called periodicity. For those who don't necessarily know how to extract that, I won't get into the big details of it, but we use something called Fourier transformation, essentially pulling the signal out of the noise. We use an 8-term model for those who are interested in that type of stuff, and if you want to talk offline, I'm happy to talk about that. And then what we use is dummy variables to determine what time of day it is, right? So we create a matrix of 1s and 0s, and we say if it's 1 o'clock in the afternoon, and that's what we're trying to predict, 1 o'clock in the afternoon is a 1, and all the other hours during the day it's 0s, right? We do the same thing for day of the week, month of the year, and then year. That word, right? So it's a big matrix of 1s and 0s that it filters through. So as I kind of move forward, I want you to just think about these 3 categories. It's a little bit more complicated than that, kind of in the inner workings of the model, but those are the 3 main determinants that we were able to find with energy consumption. And we take combinations of those variables. I'm like an 8-bit Nintendo guy, or I used to be anyway, right? And so we generated all of these different combinations of these variables, essentially a sensitivity analysis, right? Change one thing in the model, see what happens, change another thing. And we generated 6 different statistical models to be able to test what's the best combination of variables that helps us explain the most variance in energy consumption, but also thinking about it from a mean perspective, not like mean as in like capital letters, but like what's the least amount of information you can get away with would be statistically significant. So if you're an energy manager and this is kind of, nebulous, what would be the basic building blocks that you need to be able to predict your energy use at a facility or the campus level. And then we do some skill comparison and see which models kind of hit out or cross out, which one kind of ends up being the leader. So I don't want to spend too much time kind of covering the background, but I do want to talk just a little bit about how we assemble the model. So I don't just use typical linear regression where I put a bunch of independent variables into a model compared to a dependent variable, spit out a value for R squared, my coefficient of determination of explained variance, and then celebrate and move on. I'd be remiss if I didn't acknowledge that some of those variables, like periodicity and time, and even temperature, are related to one another. And when we have independent variables that are related to one another, it creates an issue that's called multilinearity, right? Which means that the independent variables are actually dependent on one another. And so I'm showing you an example of that here, where I might have like temperature on one axis and maybe like days of sunlight, days of like zero cloud opacity on the other, right? And there might be a positive relationship between those two variables. We can use an analysis technique called principal components analysis. Some of you might be familiar with that, or abbreviated PCA or PCR coming up here in a little bit, to help reduce the dimensionality of our data set. So it says, although we might have something kind of moving in one direction, we understand that there are multiple variables that might be helping us explain variability in that direction. Again, if you're interested in the details of how that works, or if you're a MATLAB or R or Python user, I can give you like one line of unpack this for all your variables. So we use that to reduce the dimensionality of the problem. So principal component regression helps us reduce the bias in the model. And then we use something called cross-validation. Because whenever you're developing a statistical model and it's actually temporally organized, meaning like you're trying to predict at subsequent time steps, if you don't take out the value you're trying to predict, right, like 1.4 kilowatt hours at 10 o'clock on a Tuesday, if you don't hide that from the model, it has a perfect target to shoot at, right? So your model is actually biased. So what we do is a progressive, stepwise, linear regression where we pull out the value we're trying to predict, hide it from it as though it never existed, right? So in those two ways, using principal component regression to limit the amount of data that we're putting into the model, and then the cross-validation eliminates the bias and some multilinearity. The only reason this is really important for us as academics is because if we want to go get this published, it's low-hanging fruit to hammer on. And then the last step we use is something called statistical bias correction. Sometimes the outputs of our model will exhibit some serial statistical bias. So if you're familiar with a probability density function and then being able to convert that to a cumulative density function where you compare the observed time series to the predicted time series, if they are shifted, right, if they are essentially aligned but shifted, meaning kind of running in parallel, we can use a simple statistical bias correction technique to make sure that we account for that as well. So again, totally in the weeds. I want to leave it behind here. Again, if you have any questions or you want to see how this all works, I'll release the code to you. I will show you the thesis. I'm an open book on this thing. So yeah, there's that. All right, so maybe a little bit into some of the results here. I apologize that this is somewhat of an eye chart. I tried to make it as big as I could while following the insertion evidence template for a presentation. So we find that climate and namely temperature and time are the variables that are most influential in energy use prediction. So essentially, the bottom line for you all is if you kind of can have an observation of temperature that matches the scale, temporal scale you're trying to predict, and you can create a W variable set, that's really all you need to be statistically significant in terms of your energy use consumption. At least for my Patterson Air Force Base, maybe things are crazy where you're at. But I want to show you kind of the intercomparison of our models. So we created something we call the collective model, and that's like throwing all the data into the model and saying, all right, sort it all out. Do principal component regression, cross-validation, statistical bias correction, and I'll kind of align you with a couple of statistics here So the first thing is the explained variance, or R squared. That's essentially the amount of variance in energy used at the half-hourly scale that we can explain. Stated in the opposite, there's about 27% of half-hourly energy use that we can't explain, right? Which is still pretty good, right? Like 75-ish% of energy use is explained. Then we also have a metric we call MAPE, which is mean absolute percent error. So when we have a forecast, right, it's like throwing a dart in a dartboard, the bullseyes that we're trying to hit, it means that our average error or distance from the correct observation when we do a forecast is about 6%. So we're not very far off as far as that goes. And then I use something called RPSS, which I wouldn't expect anybody in the group to know, which is rank probability skill score. So it's not enough just to produce a deterministic model, meaning like there's one prediction of what energy use will look like if we compare it to the model. We should create ensembles, right, to discuss or discover the uncertainty of our model and its ability to predict observations. So I create thousands of iterations of this model, essentially based off the error term between our predicted model and our forecast and our observed model. And I provide all those ensembles, and anytime that value is greater than 0, so it goes between negative infinity and 1, anytime it's greater than 0, it means that our model is better, outperforms some climatological baseline, right? Which I won't get into here, but it is better than the baseline that we compared it to, which was the best model that the base had, right? So we have their model as well. And then the only other thing I would mention here is that remember I said principal component regression kind of takes all of our variables and distills it down to very kind of nutrient-dense signatures. We can back correlate that with our original set of independent variables and figure out what's in those our new independent variables. So for our collective model, which was everything being thrown into the model, we found that the periodicity, essentially that underlying signal that we were able to define as a function, was dominating in the first principal component and then the second principal component. So essentially, if you threw everything into the model, the thing that comes out as the most important is if you have some historical record of your energy use and you can pick out the signal, you can probably explain about 75% of your energy use. Then we had kind of some scaled down models, looking at periodicity only, and then looking at climate only. And you can see that the explained variance is quite a bit lower. If we look at just the signal, it kind of underlies that it only explains about 27% of the variability. And looking at climate only, which really results in self-down to temperature, it only explains about 43% of the variation. And you can look at these other scores, but they kind of track similarly. We have a reduction in explained variance, we have an increase in our error, and a reduction in the skill of our ensemble-based models. So we kind of ruled those ones out, said the collective model was the best, at least at this point. Then we looked at the combination of periodicity and the time variables. We saw a slight improvement, as you would expect. Anytime you throw more data into a model, the R squared typically goes up. Adjusted R squared goes down for those stats nerds out there. But now we said, okay, let's take a look at another set of models here too. How about climate and periodicity and climate and time? And so what we said is, wow, you take a look at that. If I throw everything in the model, this huge collective model that requires a ton of data, a ton of time, a ton of computational capacity to solve, and I just have climate, and I just have time, going back to the sticker on the slide, I can explain just as much variance as if I have all this data. My MAPE score, so my error, essentially going to dart at the dartboard, is a little bit smaller, maybe not meaningfully so. And my rank probability skill score, my ability to kind of explain my uncertainty is about the same as well, right? So again, if you have that data, just climate and time, you can do a pretty decent job of predicting your energy consumption. But it's not enough to stop there, right? So I kind of want to start with what I've got up here on the board. So this is our energy consumption. Same plot you've seen, I just made it blue because I'm in the Air Force. And I replotted it as a probability density function, right? And so we can kind of follow the curve of that and identify 4 different energy consumption reasons. High energy consumption, I call it mid-high values, mid-low values, and then low values of energy consumption. And this is important because maybe facility managers don't care about precisely predicting it's going to be whatever, 150,000 kilowatt hours of consumption at 1 o'clock in the afternoon on a Tuesday. But maybe they care to know whether it's going to be above average, kind of average, or below average. And when I talked to the energy managers at the base, they said that would actually help them more if we could be really skillful in that direction to load shed or make no cool decisions if they had individual control of the facilities as opposed to being able to predict predict the absolute number amount of energy consumption at the installation. There's my high and there's my low energy consumption. And then we can use something called a contingency table to perform a skill assessment to say when my prediction, like for example, for this dot right here, if I'm trying to predict that dot, does it fall in the same category as that dot, right? So this is low energy consumption, the lowest on record here. Which category does it end up falling into? If it falls into that category of prediction, I end up categorizing it here. That's called hit, right? Anytime it falls at least one category away, that's called a miss, right? So if it was low, observed, and my model predicted medium low, right, I would miss by one category. And anything greater than one category miss is typically called in the literature an extreme miss. Right? So anything that kind of organizes itself on that diagonal axis from top left to bottom right ends up being our hit ratio, right? So you can kind of read that chart I was just talking about, the top left in the corner there. So when there's low energy consumption, 70% of the time, we're able to predict that it is actually in that category. You can see that we do this, we're off by one category 21% of the time. We're really only off by two categories, a combination of what is that, 8.3% of the time. How about that, public math? And that's what we really want to avoid, right? We wouldn't want to say, it's a low energy consumption period, nothing needs to be done, and it actually is a big high energy consumption period. If you're trying to manage your facilities, that's what you want to avoid. So we're able to provide some metrics like that. And that answers the question, did the forecast or model category match the observed category? And I would conclude by saying, if you look along that diagonal kind of trajectory, there are hits. Relatively speaking, right, there are many more hits than there are extreme misses. Right? So this is really key to kind of selling when you're looking to sell a product, and you're looking to convince somebody to make a different decision or manage differently than they are. This can be a really useful tool, right? And really kind of lead to So what have we learned predicting the past, right? Because that's really all it does, kind of come up with predictions in the past. We learned that our model explains about 75% of half-hourly energy consumption at the installation level. Again, that's 26,500 facilities and 30,000 people using those facilities. And we can predict variance to a level of 75%. We also found that temperature and time are most influential, but what does it really mean? It means that there could be opportunities to load shed if they can do that, right? Particularly during periods of high energy demand, specifically tied to heating and cooling, because temperature is really driving demand in facilities. And for facilities that might have low occupancy, right? So we know there are facilities that are going to make it. We have the span control to like flip the switch and turn it off. We can do that. But it requires that facilities can be individually controlled. Well, let's put a pin in that. I'll come back to that when I get kind of into my forecasting model. So now what? Predicting the past is interesting, but it's not compelling, right? Like if you don't care that you can predict your energy in the past, it doesn't really matter. You've already paid that bill, hopefully. You want to know what you should be able to do about the future, right? So what I'm providing here, and I apologize if that green isn't showing up, this is average temperature plotted historically, which is shown in green. And if you remember, I talked about those representative concentration pathways. Lots of carbon dioxide collecting in the atmosphere, and not so much carbon dioxide collecting in the atmosphere. This is courtesy of the IPCC, so the Intergovernmental Panel on Climate Change. And so if energy consumption is really related to temperature, and we expect temperature to increase, we might expect that energy consumption will increase as well. Right? So we should understand how the changing temperature could affect energy consumption. And then from my perspective, I also kind of look at economics, like what's going to be the cost. If it's a fixed budget, which it really is, where are we going to get that money from? What's it going to cost us? And we need to be able to plan for that. And so does increasing temperature necessarily mean increasing cost? Now there are a few studies out there. One was actually published in Nature recently, and they did a study across all of kind of Central Europe. And they said actually energy consumption for places like Norway, which is traditionally really cold, is going to get relatively mild, and they should actually see a reduction in total energy consumption and cost, as opposed to a place like southern Italy, which is already pretty warm, is likely to see extreme kind of increases in their energy consumption and cost. And at the continental scale, they say, we don't know what's going to happen. It'll probably just offset. Things will cross out. So it's an important question, and it's not necessarily exactly clear what's going to happen with temperature increase. What we end up observing, though, when we rerun our model with those inputs for temperature, is we see Energy consumption increases, that's what's shown here. The red is RCP 8.5, and the blue is RCP 4.5. And then the second vertical axis here shows change in cost, right? And this is in millions of dollars, right? So this would be the annual energy budget for the installation. So we aggregated all those half-hourly cost estimates to the annual cost for the installation. And what you can see is that there's about a, you probably can't tell this from the graph, but there's a 4.8 to 19.3% increase in annual energy consumption, and therefore likely cost, will cost steady energy, the cost of procuring energy, static by the end of the century. And that's a lot, right? 20% increase in energy for a base that's already probably paying a couple $1 million a month for energy. That's pretty big. Which ends up resolving itself down to about $40,000 to $107,000 per year increase. So that'd be year over year. So that's small now, but 100 years of $40,000 every year is quite a bit. And so it increases by that rate per year. And in both our cases, kind of middle of the road, RCP 4.5 and extreme case 8.5, we end up seeing positive increases in energy use and cost by the year 2050, which that's not too far away, right? Be past my career. But by the end of the century, as you can kind of see on the bumper sticker there at the top, we'd be looking at about a $2.5 to $7.5 million per year increase for Wright-Patterson Air Force Base. For those of you who do work on the Air Force Base or you understand how military construction works, that's a no-time project, right? That's a big for an installation. And they might only get every 5 to 10 years. And then if you think of the enterprise level, beyond just the Wright-Patterson, you get to other installations, that's no-time projects across the Air Force and across the DoD that can't be built just because we're failing to act on increases in energy consumption across the system. So kind of digging a little bit deeper, I've got some box plots here. This isn't my favorite plot, but it's what I had to work with. What's going to happen during the year? So thinking inside the year, what's going to happen in terms of our months? So I have months shown across the x-axis there, RCP 4.5 on the left and RCP 8.5, and then I'm showing a change in energy consumption in gigawatt hours on the vertical axis there. And what you can see, and I'll kind of do my reveal here, is that there's much less certainty in RCP 4.5, right? The box plots of what's happening, the change between 2030 and 2020 and 2030, the next decade, and from 2030 to the end of the century, which is what I'm comparing here, is much less certain, right? They overlap significantly. So it's hard to say what's going to happen if we follow kind of the middle of the road carbon future. And that's precisely because there's less temperature increase, right? And there's also much less certainty in both RCP 4.5 and 8.5 in the winter time frame. The winters become more mild, but are they mild enough to shut off? Probably not, right? Which is what we're seeing here. However, there's clear dominance in the summer in terms of the upward trend, particularly in 8.5. So once you get into, eventually May will be summer here, at least if you kind of trust the data, right? May all the way through September is going to be your summertime frame, and you can see that the energy consumption by the end of the century will be much higher. But even in the near term, in the next 10 years, right, comparing what we think energy consumption will be over the next 9 years, or 8 years, to the next century, there's still a market increase in 8.5, just because of the temperature increase. But the change significance improves by the end of the century. So what I'm showing here is a table that looks at each month, right, which is shown on the rows here. And then the columns show the decades, right? And every time that there is a darker color, that says that we have a statistically significant relationship, right? So, and you can see the different p-values, right? Typically, if you read a paper, it's like p less than 0.05 is the gold standard for anything, right? So this would be, we're 95% confident there will be a positive change in energy consumption, right? If there's a negative sign, which I think there are just a couple, right? Kind of down here and up at your winter seasons in RCP 4.5, we are somewhat confident, 75% confident, that there will be a negative shift, at least for that decade. But what we notice, if you kind of draw some inflection points here, it really looks like if you're looking at 4.5, kind of middle of the road, we see that there's kind of some statistically significant changes in a positive shift in energy consumption. If we follow a 4.5 track between 2050 and 2060, kind of getting into 2060, 2070, as opposed to RCP 8.5, it probably happens a decade earlier, right, where we see consistent positive changes month to month in energy consumption and costs associated. The last kind of plot that I want to bring up here is the cost change variability, right? And so what I'm showing here is, and I don't know what's kind of in the background here, but there's a change in cost in thousands of dollars across the line. What we've done is based off of our ensembles, we've plotted percentiles, right? So what is the 25th percentile change that's shown in red, the median change is shown in green, and then the 75th percentile change is shown in blue. But what I would draw your eye to is that this line here represents a positive change, right? Anything above that. So essentially, if you look at 2090 to 2100, so many years from now, as opposed to 2050 to 2060, you can see that there's a drastic change in our expectations of energy consumption, right? So at the 25th percentile, we'd be saying, even in a year where there's not a lot of, like warm spells or really cold spells, even at the 25th percentile, we would expect to see hundreds of thousands of dollars in energy cost increases, right? And so I show this to show you that we've done some uncertainty analysis on this as well, that our future models are not deterministic. So we kind of look at the interquartile range between the 25th and 75th percentile, and we should expect to see some energy cost increases. So the energy consumption and costs are expected to rise. This is kind of drawing to a close here. And our facility energy operating budgets, or our facility operating budgets, kind of as an umbrella term, do not keep pace what could and or should be done. And I'm sure there are some of you that have ideas in this room. And are there mixtures of what I'll call hard and soft adaptations that can stabilize your operating budgets? So hard adaptation would be something like installing a photovoltaic system, as opposed to something that would be soft, which would be something like a policy. And many Air Force bases and DoD bases have instituted what they call locally no heat, no cool seasons during the shoulder seasons, right? So like, maybe October 15th, that was just like shut all the HVAC off, all the chillers off, right? And then they go to a period where they're only using the air handlers to just kind of blow ambient air from outside into the facility and do the exchange, and then maybe November 15th they can be done, right? So a policy like that, it doesn't really cost much to implement, but can provide some energy savings, although it's probably uncomfortable. Okay, so let's talk a little bit about hard adaptations that exist. So this is a software package called Homer. Some of you might be familiar with this. And really what Homer does is it sizes a photovoltaic system and it tells you what the output is going to be for that system based off the climate data that you input. So like solar radiation, essentially how much of the sun's rays are getting to the earth, temperature, wind speed, cloud opacity, things like that, to be able to size a photovoltaic system to be able to offset their emissions. So we have a project that's currently underway. That is kind of the next phase of this project that says, given the fact that we expect a $2 to $7 million increase in energy consumption over the remainder of the century, is it economically feasible to install a photovoltaic system on all the land area that we have available at right that to offset those costs? Does the cost benefit ratio is positive? And so we have to kind of consider how this thing is going to change over time. And then we also have soft adaptations that we could implement. And this came from a study that my colleagues and I published a couple of years ago, where we looked at implementing a no heat, no cool season for several installations across the contiguous United States. And the coloring on the map here for the U.S. is based off of something that's called the Köppen-Geiger scale that kind of just classifies areas of the country as to whether they're temperate, whether they're polar, whether they're cold. You can kind of see the scale over there for that heat. And then what we looked at is we said if we were to implement a no heat, no cool season at about 70 degrees, daily average temperature for 5 days is kind of the threshold to turn things on as we come into the summertime and then off again as we come out of summer and then turn the heat on in the wintertime, and kind of measure the number of days in those shoulder seasons when you really need heating or cooling. What we noticed, of course we looked at right path, is we saw a shift in the amount of heating and cooling demand, right? In the near term, so this is this decade, we saw significantly more heating and cooling demand, and then we see that shift over time. And the number of the heat to cool and cool to heat kind of shoulder seasons, when we would require heating changes significantly. We go from something like, I know you can't read it there, it goes from like about 75 days of no heat and cool all the way down to about 20 days when we kind of cross through that threshold. And you can kind of see that here in the plot here where I have, this is kind of the temperature signature throughout the year, this black, mid-century is this gray, and then this really light gray is how we expect temperature to change kind of throughout the end of the century, the last decade. And these blocks are meant to represent kind of that transition season. So as temperature starts to become more steep, You can see it's still kind of a normal distribution, but as it becomes steeper, we transition through that no cool zone, that window of opportunity a lot faster. Okay? So there are going to be less opportunities for something like this, like soft policy, to be the solution to our problem as we move on through the rest of the century. And so the takeaway from that is, and this kind of permeates a lot of the research that folks are doing in like how do we not necessarily mitigate, but account for climate change and how we operate, is that we can implement soft policies now as a kind of wait and see, right? Because we're not, I mean, if you go back to that plot where I showed the different RCPs, it's like no change, max change. It's like highly uncertain what's going to happen. But if you implement a soft policy, it costs you really not much to do it right now. You can kind of kick the can down the road and potentially get some savings now and wait to kind of see, hey, is it really the right time to install a photovoltaic system, right? But if you analyze both of those at the same time, you can assess the option value, if you're not familiar with that term. So just kind of some opportunities, right? The other thing I talk about too, and some folks have probably seen this better on the Air Force Base and Office of Civil Engineering, we call this the installation or the infrastructure health assessment, the IHA. And we call this the virus chart. And so recently the Air Force has gone through and thought about all of its facilities, not just from a condition perspective, but they've thought about it from a mission dependency. Essentially, how important is the mission that emanates from this facility? And so what I'm organizing these by here is by major commands, so different combat commands or location commands, like this is specific air forces here. And each one of those pixels corresponds to the condition of a facility organized by its importance. Right? So everything to the right is essentially facilities that are in failure status, right? That are in red. And they are low value assets for the Air Force. And everything coming to the right would be higher value assets for the Air Force. And you notice that we already kind of do a decent job at trying to keep our important facilities in good condition. But it brings up the question, do we divest of certain facilities to draw down our energy consumption as well? And that effort's kind of underway. I was talking with some folks from Headquarters Air Force, and they're looking at what they're calling intensive community basing, getting rid of community support facilities that are available on the market. Right? I can count, I can't throw a rock without hitting a child care center outside of like Henderson Air Force Base. Yet we have 2 on the installation. So they're looking at opportunities like that to curb energy consumption as well. But the other thing too is that even if we were to get something like $2.1 billion in sustainment funding, it doesn't fix what I told our facility sustainment, restoration, and modernization backlog. So even if they continue to give us what they've always given us, $2.1 billion a year, your money, really my money too, I think taxes as well, it still doesn't fix the problem. We have a huge backlog, and that's 2047. So there's some big problems to sort through. It's not just energy consumption, it's facility condition, who divest, how do we make those decisions. So just a couple more slides here, limitations and conclusions. What do I think the model is capable of? Well, one, predicting finely resolved temporal energy use. I can make half-hourly predictions of energy use for an installation that has 30,000 people at it. That to me looks good. We can also forecast the future demand and potential for cost change, right? Uncertainty and all that stuff. And so I think we've done our due diligence there. However, the question is, like, let's bring it back to reality. If you're a facility manager, does it really change anything for you as a facility manager? If I can be skillful at predicting half-hourly energy consumption to you, does it really force you to do anything different? And does the utility of what we produced here depend on the level of your span of control? I'll answer those kind of on the next slide here. But here's some limitations. Based on our calibrated model, there's still about 25% of unexplained variance. And as we look out further, as temperature becomes less certain, that explained variance drops and the unexplained variance actually rises. So that's something to consider. And then the other thing too is we held the cost and the size of the installation constant. Right? So I'm not at liberty to reveal what Patterson pays for energy. And what mission sets are there, but we held those constant, right? But we always need to presume that the cost of energy is likely to increase, and that the base is likely going to expand, right? That AFA just did a master plan study, and we have plans to expand, not shocking. So that's a limitation here. This is a very conservative estimate. So is it worth it, right? Coming back to the basic question we said I was going to answer. Is it worth it for you to install meters at every single facility? Personally, I think this study reveals that it's it's likely not the best idea unless you have one, the means to actually install them. Second, the knowledge, and then third, the authority to control your systems, right? So can you actually, kind of getting after the means, can the systems actually be centrally controlled, right? Because in a lot of places, like even right Patterson Air Force Base, 26,500 facilities under installation, almost none of them can be individually controlled. So installing meters at the facilities and collecting that data is a waste of time, it's a waste of money, it's a waste of energy, right? To collect all that data because you can't do anything. Second, you understand how your people and systems use energy. You have the knowledge of what's, even if you can kind of satisfy constraint number one, do you actually know what's going on at building, 110 to be able to install like a EMCS, an energy management control system, to be able to toggle power off and on and reduce power and things like that throughout the day. And then third, you have the authority. Like certainly, I'm an engineer, I have the authority to do nothing. I have lots of responsibility, I'm culpable for lots of things, but I am not a decision maker. And I know that, they remind me of that all the time. But I don't have the authority to manage my energy use through systems or policies, but certainly the main commander, right, as a pilot, has the ability to manage that. So if I don't have all three of those, maybe it's not such a good idea. And even if you do, you need to consider the granularity at which you collect the data, because we're paying for that 30-minute data, but we're not doing it. The energy managers aren't. They said, here's all our data, and I was like, holy cow, you have 30-minute data, what are you doing with this data? I was like, there's probably no way I can help you, because you're collecting 30-minute data, you must be doing something with it. And they're like, well, nope, it's just data that we have, right? So, and they can't manage at that scale. Like I told you, the base goes through like a transition season where the HVAC techs come out to every installation, they shut down the chillers, they turn the boilers on. It's like a week and a half throughout the installation where everybody's sweltering, right? Because it's just too hot, or in the springtime it's too cold inside the facility. So it's kind of, it creates problems. So why are we paying for 30-minute energy data if we can't really control at that level? Non-attribution. So, I mean, I guess I would leave you with that, right? Consider what your ability to control things is. Do you really need to chase the kind of gets after this Costello's point? Do you really need to chase the bright, shiny new technology if it ultimately won't help you make better decisions? I'd be remiss if I didn't mention the people who actually did this work. I advised it, but that's just kind of like pointing and people doing stuff. So Captain Scott Weiss, who's actually out in Grand Forks right now, PCS, he's out there, he was the student who put this together. But also my co-collaborators, Lieutenant Colonel Steve Schultz, who's now the commander out at the Civil Engineers Squadron Commander at Bowling Air Force Base in the DC area, and then Dr. Chris Cheney, who I work with, our civilian faculty. This work was sponsored by the Air Force Civil Engineers Center, obviously by AFIT, and the Air Force Energy Agency as well. I'll leave my contact information out there if you're interested in this type of work. Please reach out to me. I'm happy to look the thesis that was written on this and also the draft manuscript that we have that's kind of in review right now. I'm happy to release all that information to you to help you plan out your help you model if you really want to use the model. With that, I will yield the remainder of my time to the moderator to take any questions. Yes, sir.
So, literally, they will shut down the HVAC cooling for a predetermined time. So the technicians will come out to certain buildings and just literally shut it down and let the ventilation continue.
Yep. So at some bases, and I showed that map where I showed you the heat and cool season, right? Like that kind of bar chart with the red, blue, purple. There are some bases, like especially overseas, where they pay like $1 million for energy. Like Kunsai in South Korea. We shut down our HVAC on April 15th, and it doesn't get turned back on until May 15th. Every year. And then we do it again October 15th, and don't turn it on until November 15th. So for 60 days out of the year, the only thing that's running inside the facilities, HVAC-wise, is the air filters. Right? To just bring in outside air and then flush it back out. As a way of saving money. It does, if you talk to the energy managers, you're saving, it's not much, right? But $100,000, $150,000 a year. Granted, that base is 2,500 units, so 110, we're going to make it too less.
You pick and choose what building you shut down, right? It's not just across the board and building off.
You're right, yes. So there are some buildings like core common facilities that have like, I dependence with comm. So let's say mainframes, like huge data computing centers that require like they have really specific HVAC tolerances. So there is an exemption list. But on our path, they don't have an heat policy. So it's just there's 30,000 facilities, and it takes the HVAC technicians a while to get around to all of them. And so there's like a day where your facility won't have any heat included in it. So it's not uniformly applied across the Air Force or the DoD, at least right now. And people hate it, right? It's hot.
Yeah.
Or it's like, bring a jacket to work, last week. Questions? Anybody else? Yes, sir?
Well, how do you count for those days, the historical days that you couldn't launch? For those days or maybe days that other load shedding reasons?
So we don't directly. And so I'm glad that you asked that, but I was hoping you wouldn't. So those are mostly our extreme misses, right? So remember on that contingency table I showed, like cells coded in red, as we want to avoid these extreme misses. That's typically when we're achieving those misses. It's during those days where like the HVAC section is out there like pulling levers. I imagine them out there with like big wrenches, like turning you guys like that might be the truth or not. But those are the days that we're missing mostly. So we don't account for them. We say we're just going to kind of roll it from the model. But when you have 35,600 data points, those don't significantly affect the skill of the model. If we were looking month by month, year by year, you would see the shoulder seasons were not as good. Other questions?
So I'm assuming then that you don't have subunitary data available, because it sounds like climate, periodicity, and time are your biggest factor variables for determining predictability. HVAC is a huge driver of that. So if you had subunitary data, I'm just curious if you looked at it just with subsets of energy usage rather than whole building or whole campus master meter data.
Yep. So talking to the energy management folks that have like a crew of like 3 or 4 people who sit in the civil engineer squad and they're doing energy management. They receive 3 bills, one for area A, one for area B, and then they have like some substation. And even if there is some build, like at the building level or even sub-building like asset monitoring, they're not collecting over time. Maybe the data is being collected, but they don't retain it. But if you look at, there's quite a bit of literature out there to kind of try and answer your question. If you're trying to understand the relationship between energy use at the facility level and HVAC, they say it usually accounts for, especially in peak seasons, about 40 to 60% of energy use is the heating and cooling of the facilities. More during the summer and less during the winter. But a lot of it depends on like what your system is, right? So they may have like 15 or 20 EMCSs, so these energy management control systems, and almost none of them function any longer, right? So we pay for stuff, we pay for technology, we never use it. So sorry, I don't have a great answer for that.
Yeah, I'm just curious if you ran an iteration where you only looked at submeter data.
Yeah, maybe it exists, but it was really not. It took a while. I'm surprised they even wanted to show you a lot of the energy use. DoD is the biggest consumer of energy by the way, guys.
Do you have a central plant or out there serving all these buildings, or do you have individual systems on them?
Yeah, good question. So as far as the electricity goes, it comes on base commercial, right? There's plenty of substations around the base for the electricity. Specifically, the base gets its heat through a steam plant. Couple. There's one kind of by the King Hawk Annex, which is kind of in the Fairborn. And then there's one on National Road in 444, kind of by area. If you've been by the Wright Memorial at all, there's one there. And so that used to be coal driven, right? They were bringing literally tray cars of coal and dumping there, and then they burn it. And in 2015, they did a conversion to natural gas. There's still a little bit of coal being burned, but it's mostly those 2 natural gas plants that provide steam, force heat to the entire base, and then there's electricity that provides some of the heat, but most of that is like raw level, like commercial power plants. But go ahead.
Cooling?
Chillers, like decentralized chillers on those facilities.
Decentralized, okay.
Yeah, on those facilities like in our building, which holds 350 people, 4-story building. The Delorit died, and so Yeah, most is like packaged units on top of it, so there's just light spaces along it around the days. Winter's easy, right? They just shut the plants down, then they got to go around and turn on all the cooling systems.
Okay, thank you.
Yes, sir. Other questions?
I came in a minute late, maybe I was a little confused about what defines a facility? Just from the point that I noticed you got 30,000 people and 26,500 facilities. It seems
Yeah, so a little bit misleading there. So yeah, it's a good question. So a facility would be defined as anything on an Air Force base that has a number attached to it, a street number attached to it. That could be something as simple as like a party, right? So like an unheated, uncooled, like essentially like a picnic canopy, right? So 26,000, I guess, is maybe a little misleading. I know there's far fewer facilities that are actually heated and cooled, and I wish I would have thought of that before I came here, and I apologize that numbers are a little misleading. Most places, like for example, like a place like Kunsam, an order of magnitude less people, right, had 800 facilities for 2,000 people, so maybe that kind of gives you an idea of the ratio. Heated and cooled facilities. It's still a lot. Oh yeah.
it's only about a year per facility.
Oh yeah. But yeah, I could definitely. I just did a master plan for Air Force Institute of Technology, and there's some MUDA, there's some waste definitely going on in terms of facilities. Trying to do that. Other questions? Empire, you know, right? People they put down roots and then